Okay, hi. This is a recorded class for Wednesday, April 7th for Polymer Physics. Um, so, see, I started to talk about hydrodynamic, how to use dynamic light scattering in the last class. I wanted to finish that up today and then mention a couple other related techniques. Diffusive wave spectroscopy and quasi-elastic neutron scattering that are related to dynamic light scattering. I kind of rearranged these slides to talk about correlation functions first. So this is from this book by Tadmore and Gogas. Just a polymer processing book, which it's on the web page. See if I can just open it here. It'll be faster. So they go through. They have a chapter on mixing, which is it's pretty physicsy. It's a polymer. Processing book, so they go through a lot of rheology and different shear fields and things, but they go into in depth in this mixing chapter. It's a book. It's a little bit old. I guess the second edition came out in 2010 or something, but the original is older than that. 2006 was the second edition, and the first edition was in the 80s, I think, 78. So there's a lot in this book. So melting, let's see, mixing is 322. Right, so somewhere around the middle end of the thing. I guess not. It's actually directly the middle. This is a pretty comprehensive book. I like the part about the mixing chapter though, because they really explain like how you can use physics in processing. Right, so they talk about how things break apart and shear fields. Last time I showed you that laminar flow is reversible. This kind of stretching the shear flow in a laminar flow is reversible. And you can reverse this kind of phenomenon, like breaking up and then going back. But the thing you can't reverse is diffusion. When things start to diffuse, he's showing like how mixing happens in different conditions, and then it's a lot of math. It's a good book. This is a pretty good book, and the mixing part is really pretty good because they've studied Brabender mixers and like look at the cross section or through an extruder, what the cross section of the mixing zones are and things. It's worth taking a look at this if you're working in the polymer field, right? In extrusion or any kind of processing type application. But anyway, then they get to the math of mixing, like how things break up and disperse, right? It's basically a branch of physics. And it's becoming even more and more a branch of physics as soft physics kind of moves into the mainstream of physics. So anyway, it's worth flipping through that book if you get a chance. So in terms of this correlation function, it's a way you talk about dispersed systems. If you have a system that seems to be disordered, you want to determine, is it really disordered or not? You calculate the correlation function. So one way to do it is to dart throw. So you have some kind of odd structure. You gotta throw darts in it. So basically, you're gonna take 2 points that are separated by a distance r. Let me shrink this. And so you have your material, some field of view, and then you're gonna take darts and throw like dart, meaning you're gonna put an arrow into the bigger random, right? And then sometimes, so they're all the same length r, and sometimes the r falls within a phase, so the two ends are in the phase, and that counts 1. this counts 0, this counts 0, right? And you're going to sum up all those conditions. And then you're going to get some function as a normalized function. So it'll be 1. So if r is length is 0, then it's going to be 100% in the, that both ends would be in the particle. So g of r would go from 1. And then as you go out in r, if it's really a random system, it's going to have like this exponential curve, right? Some kind of length. So this is like the scale of segregation would be that length, like how quickly does this decay? So when this is when r equals that length, then this g of r equals e, right? Since value's e when you're at this length. So, or 1 over e, sorry, so it's going to be like 0.27 when you're at that length, L, this kind of average length. And that length's a measure of the segregation of the system. Right? So, so these are all different. So you throw in a rod with 0 length, which is a dot, then you just get the concentration. So you normalize this kind of sum by the concentration squared, because it's 2 points. So that's how you normalize it, by the concentration squared. And then it's going to be this decay function, you get that length, right? So it shows that that behavior can be used to look at different kinds. Even this is like garbage bag, and you put color in it and you want it to be uniform, but basically you get streaks. So you can characterize these streaks by this correlation function, right? This is the correlation function. You take the concentration at 2 points, or say your concentration minus the average concentration at 2 points separated by a distance r, then sum up over all possible 2 points in the system and divide by the square of the concentration. Then you'll get this correlation function, right? And then the integral of that gives you this scale of segregation, or you could fit that to an exponential and get the this average length, right? So this just shows that this kind of correlation function analysis converts space, right, to kind of inverse space. So that would add a length. So you take space, which would be r, and it's kind of converting it to q. Q is kind of an inverse space. So this process is the same thing as basically a Fourier transform. So you're finding, say, if there's a bunch of sine waves in this data, then you come out with sine waves here. Right? So any data can kind of be represented by sine waves. So the relationship between this noise pattern and the amplitude pattern versus frequency is the Fourier transform. It's going to be try to fit sine waves to this. The amplitude of the sine waves versus their frequency is going to be this pattern. Right? So this noise pattern can be decomposed into a series of sine waves with like these frequencies, these amplitudes. Right? So that's like the idea of this. Anyway, so what does that have to do with dynamic light scattering? Well, in dynamic light scattering, you're going to take a laser and shoot it at a sample, and then you're going to see a speckle pattern come out of this, which I have somewhere here. So on slide 31, I put in. So this is Paul Russo. He's the guy that he's one of the best dynamic light scattering guys around. He's kind of the second generation of dynamic light scattering. He had Ben Chu at Stony Brook in New York, and then some people at UMass and Amherst. And then Russo came along and kind of studied with those people. And then he was the next generation. He's also a chemist. It's kind of a material science and chemist. The speckle pattern here, there it was. View speckle pattern. So just grab that guy. Hopefully this works. Actually, I didn't check this, but it's just a video of what the speckle pattern is, if it works. Basically, the laser, because laser has a special features, it's monochromatic, so lambda is fixed, and it's collimated. So of these two, so if the lambda isn't fixed, then the beam will self-destruct, right? It has a coherence length. So if it's not a single wavelength, the waves destructively interfere and it will annihilate over a certain distance, right? So that's called coherency. So the different waves that are within a beam of light can be at different wavelengths, and they'll interfere with each other. So the light can only progress so far before it annihilates itself. So you can see in this video, this thing is flickering. That's called the speckle pattern. So each dot has to do with a particle kind of flying through the beam, right? And the particle appears and then flies out, so the light shows up and disappears. So that flickering, you can only see with a coherent radiation. In other words, all the waves of the radiation. I wonder if I can get this to repeat somewhere here. It's probably a button that does that, but so all the so it's flickering. You can see there's a size scale. There's a ring here associated with the size scale of the particles. So these are spherical particles, and the scattering pattern. So you look at like intensity versus Q for a sphere. It's going to have like a bunch of peaks that have to do with this fixed perfect size of the sphere, the diameter. And so 2 pi over that Q gives you kind of the diameter of the sphere. Sorry. I don't need that anymore. So anyway, let's see, and I was on 31 before here. So so there's a size scale of the sphere that shows up, and then there's a speckle pattern that has to do with the particles flying through the beam. So it's on and then it's off. It's off, on, off. So it blinks. Get this blinking, right? So the intensity at a given Q, maybe you'd take the Q for that peak because that has to do with the sphere diameter. So you take the Q here. So you'd set up your detector at a fixed angle, maybe at that peak. Then you just watch how it flickers. So it's flickering. And that flickering has to do with how fast the bead is moving through, and how fast it's moving through has to do with the diffusion coefficient, right? It's being driven by KT, and it's being slowed down by the viscosity. And the ratio of the KT to the viscosity gives you kind of a time, right? A speed. So basically, the rate of flickering is going to tell you the diffusion coefficient of this thing. And so they invented the laser kind of in the 1960s. I mean, it became that you could buy one, right? And then probably 10 years after that, people figured out that you could do some things with lasers that you couldn't do with other kinds of light sources because they were monochromatic. So there's a fixed wavelength. No, it's any other light source, like take a light bulb and it's going to have a spectrum. If you plot the number versus wavelength, it's going to have some kind of spectrum. That's the emission spectrum of the metal that you're looking at, right? But a laser, because it's a confined electrons kind of generating the light, and there's a quantum effect, so it's fixed energy that's generating the light. So basically, it's single wavelength. This is a single event giving the light, single energy event. I said monochromatic, and also because of the way it's produced, kind of in a chamber, all the light's in phase. So it's in phase. So it's coherent, meaning that if you had, say you had monochromatic red light that you somehow filtered out of an incandescent bulb, well, that light would only progress so far because the waves would be out of phase and they would destroy themselves. They would destroy themselves. Basically, the coherence length is a measure of this coherency, which is also an exponential decay. So it'd be like the L for how long it takes to decay. For a flashlight is something like a centimeter or less, right? And the coherence length for a laser is going to be like 50 meters or 100 meters. That means you can shine this laser across your yard and hit a tree on the other side, right? So they have these Christmas lights that shoot up into the trees. Or you can run it around the room and the cat will chase a red dot, right? So you can't do that with a flashlight because the light, one thing is it's not collimated. So the laser is also collimated. So all the beams are going in a straight line. Normal lights are radiating out. So you get 1 over r squared decay. And it also makes a diffuse footprint. So you don't see the beam So it's coherent, it's collimated, and it's monochromatic. Those are unique things. You need all three of those to get a speckle pattern. So before they had a laser, you couldn't do this, right? So basically, with a laser, you can suddenly do this kind of thing. You can watch this flickering of the light. And if you can watch the flickering of light, this looks a lot like our noise pattern, this noise pattern, right? So you can do a correlation function analysis of it. So the problem with this is that you want to take the correlation between any 2 points in this separated by a time t. You want to do that from t to 0 to infinity as the thing's running, right? So if you generate a data set like this over an hour, and then you take all the data points you have and you calculate this. So it will take a computer, even a modern computer will take it a day, right? It'll take it a day to calculate the correlation function from all that data because there's too many points. There's going to be millions of points and you have to correlate each one, and you have to correlate them more than once. You have to correlate them for every time separation distance you want from the whole experiment down to the sampling time, right? So that takes forever. So the people at the beginning in the 70s figured out that they could build an electronic circuit called a correlator that would do this instantaneously. And they did that. So that was a big coup. Once they had correlators, then you could just generate this correlation function from that data, that noise data. So the correlation function, again, is going to be the dot product of the intensities that separated by time t, right? And then the t prime is integrated over all time from minus time to time. Then you normalize by the time gap. Then you get this, what's called the second order correlation function. It's not normalized because you haven't divided by I squared, right? So it'd be like you have to divide by the average value squared, what you would get when t is 0. And then, so you can get this G2 almost instantly in a dynamic light scattering machine. What would have taken like a very long time to get? You can get instantly because they figured out how to wire this through the magic electronics. So that G2's got two components. I mean, it's got a flat background. I mean, the square. So the thing you get when time's 0, which is going to be 1 if you normalize it, and then it's got the fluctuation part, right? So the fluctuation part is the part you're interested in. So that's G1, and then G1 is basically going to be the same thing as this exponential decay that we had for the spatial correlation function. And you're going to get some number out of this, which is kind of the correlation length of the thing. In this case, it's going to be a time, tau. So it's a relaxation time. So T over tau is relaxation time. And if it's Brownian motion, so if you're looking at Brownian motion, then you know that for Brownian motion, the mean squared displacement equals some constant, which is a diffusion constant times time. Okay, that's the definition of Brownian motion. It's also the definition of the diffusion coefficient. So that means that this is like the average of r squared, right? So that means the distance you travel is going to be with time to the 1/2. Or if we're looking at q equals 2 pi over r. So if you say an r squared, then everything's squared, and then you're looking at q squared because you're doing a scattering experiment, right? So you have to consider that this r squared is going to go with the diffusion coefficient. So it's going to be like d over r squared, and r squared is inverse to q, so it's going to be q squared d. So that 2 means Brownian motion. If it's not 2, then it's not Brownian motion. So if you plot log of tau versus log of q, then you're hoping that this thing is going to have a slope of 2, right? So it should go -2. Sorry, it should go like that. So things get faster when they get smaller. Right? If it's not -2, so say it's ballistic motion, like you shoot a bullet and it flies in a straight line, that slope will be -1. Right? So you can tell if it follows this power 2 dependence. So you can measure tau directly, right? Gamma, capital gamma, you get just from the measurement. Then you can plot gamma as a function of Q and find out, is it Brownian motion or not, right? And if it's 2, it's Brownian motion. If it's 1, it's ballistic. And if it's something else, it's something else. Right, so you can talk about like what kind of motion is going on in the system. Basically, this is going to be used for the most part to get the hydrodynamic radius, right? So the assumption is going to be that it's Brownian motion. So you can check that by measuring at a couple different angles, and then once you get that, you're going to see the machine will spit out. This is from Paul Russo's lab that he gave for his class, but so I'm just copying some of his things. It's simple. This can be plotted in different ways, but since it's an exponential, so you're expecting that e to the minus t over tau is going to be your G1 or G2, right? So you're expecting to see like log of G is going to be linear in t, right? And then this gamma is going to be the prefactor for it. So if you plot log of G versus t, it'll be a straight line. And as you go out to higher t, there's less possibility to sample because you've measured your noise pattern over a certain length of time, right? So you say, I want my R to be that length of time. There's only one. That's the total length, right? Whereas if I have this small one, then there's a lot of them, right? So the smaller times have better statistics than the high times, right? And in order to get better statistics here, you'd have to run for like 10 times that length of time. And so that's why the noise shows up here, and the statistics are good at the low end. Anyway, this just means it's an exponential decay. Then you look at the prefactor you get from that and do log versus Q to see if it's Brownian motion. Right, so that's kind of the idea of this. Usually this is the plot people show, like G versus log T, which shows this kind of inflection point that gives you an idea like where is this relaxation time in this thing. Like here, this doesn't tell you where the relaxation time is, and this kind of does. So you can tell it's an exponential decay, and that tau is going to be like kind of where that arrow is. Right, so there's different ways to plot it. That's all that's saying. Anyway, this is the Einstein-Stokes equation. So Stokes' law is this friction factor, 6 pi viscosity times the particle size. And then KT is driving the motion, and this is slowing down the motion. So the ratio of those two ends up giving you a size, which is the hydrodynamic radius, which is the radius of a sphere if the particles are spheres. It's the radius of an equivalent sphere if the particles aren't spheres. So this is what Russo says about it, just that they're like spheres. So one thing you could stick in this machine is any kind of colloidal solution. So you can put in milk, which is a bunch of fat vesicles. So milk's a bunch of vesicles, kind of a surfactant. So you have polar groups and then non-polar alkane groups sticking off, and they'll form like a big sac, basically. They'll form micelles, but if you put in some proteins in here, then they'll just surround the proteins and form a sac, which is called a vesicle. And the vesicle can be like a micron, 1 to 10 micron size. And that's what, since these are charged on the surface and they're in water, then you can solubilize the fat and you make something like milk, right? So basically, this thing's going to be a bunch of these odd-shaped vesicles floating around. And you can get kind of what's the tau, what's the relaxation time from motion of those vesicles, and that's going to give you the size of the vesicle, the hydrodynamic size of the vesicle from this. So D, it's too bad that he used D here. He should have used RH, because he's got diffusion coefficient and he's got D, so he's already used D. You can't use D again. So anyway, that's what Russo did. All right, so milk. This is the if you use, so you can do a more elaborate analysis than just one RH. So you can use multi-culminant analysis. So you have many of these exponentials summed together to give that decay. If it's polydispersed, then you can get a particle size distribution from that in terms of the hydrodynamic radius. And these are different kinds of milk, showing that the vesicles are different size in them. Because when you take out the fat, I mean, you're removing the vesicles basically. The vesicles contain the fat, so you kind of, as you make it more and more skim milk, you're taking out the larger vesicles and slimming it down, right? So anyway, so that's, you can put a lot of different things in here. You can put a polymer in, so you can measure sizes down to so your wavelength of light is going to be 0.6 micron, right? But because you're not using that size, so that would be about the size you could measure with light, like about 1 micron with a laser from a scattering experiment. You can't measure smaller, but with this measurement, okay, because you're not looking at the Q scale, except in terms of how far the particle moved, you're looking at the time scale, the time of the flickers. The time of the flickers you can measure on a millisecond scale. If you figure out what the millisecond equivalent is to the diffusion coefficient, in other words, through this equation, what does 1 millisecond mean for tau in terms of D and then in terms of RH? Oh, that is D, sorry, RH is here. Sorry, I got that confused. So RH is here. I was looking at this and I was trying to find, because 6 pi viscosity times RH is Stokes' law. Then that equals the diffusion coefficient. We swapped out RH and D. Sorry about that. Then anyway, so the size scale you can measure in terms of time in a millisecond scale resolution or less, depending on how fast your correlator is. This thing can be angstroms. So you can use light, which is 0.6 micron, and you can measure something 1,000 times smaller, all the way up to, so the range of sizes you can measure is going to be orders of magnitude, so all the way up to microns or larger. Right, so since you're just looking at the time flicker, I mean, it's just basically you can measure huge sizes or small sizes. And the small sizes are easier to measure because they're faster, so you're going to get better statistics. The faster it is, the better statistics. So it's actually easier to measure small things than it is large things. Large things you have to measure for much longer time. Right, so there's a lot you can do with this. If you put soap in, you get multiple. So soap is going to have these form like micelles. If you put soap in, you get a diffusion coefficient for that direction and one for that direction. So you get 2 decays. Like the decay will be like this, 2 steps. We plot G1 versus time. Right, there'll be like 2 separate steps. One's like a lateral motion, one's a that motion. So asymmetric particles will display 2 relaxation times. You can pick out a lot of information from this machine, and it's really easy to use as long as you keep things clean. So dust and dirt are going to be your enemy in this. So that's kind of how this works. So you should know this, like you should probably know this, since this is an easy tool to use and really easy to use, then you basically should know about this machine. You know, you should know how to use it, what it is, and how it works. The math is a little bit, you know, it's a little bit of math, but it's not too bad. This is a correlation typical display. This is from the machine that we have in the Materials Characterization Center. This is the noise. It shows the noise pattern that's coming out, intensity at some angle. The angle here is sample n. I think these curves are 0. I don't see the angle here. Anyway, usually it's 90 degrees. That's like typical for this. And then there's the relaxation time. It's coming in at 1500 hertz. So that means that it's 1 over that. So that's milliseconds, right? That you're talking about. So it's 1 over 1500. So it's 0.6 milliseconds. Right, so again, like the time, you can measure these really small times. That means you can get angstrom scales. That's going to be something on the order of like 51 nanometer, 10 nanometers. Right, so you can measure things you would see like in a TEM in water. So while they're in solution, right? So there's a huge advantage to this. This is the only technique where you can see nanoscale with light. Right? So it's a big advantage. So anyway, so there's other techniques that have kind of ridden off of this thing, right? And one is called microrheology. So traditional rheology, you have this would be like typical Couette viscometers. These are like Couette viscometers you use in the lab to look at solution samples. Then these would be like melt rheometers, would be cone and plate and plate and plate. And basically oscillatory rheometry, we oscillate this back and forth, and these are usually used with the continuous rheometry. So it's continuously moves around. This one you get G prime, G double prime. This you just get the viscosity, like one number. But you can do it as a function of the speed of spinning and the temperature. So I'll have a water bath on it. You'll be looking at basically something like a biological sample in these, right? And these things are more for melt viscometry. So there's another, but there's a limit to the frequency, to the speed that you can do this, either frequency or rotational speed, because there's a breakdown at the wall, so you get wall slip. So if you want to get really high frequency or really high spinning speed, there's a big problem with these, right? These don't work anymore because once you get wall slip, the number isn't realistic, right? So for mechanical rheometry, there's limits at high frequency. And you want to know high frequency because that's where a lot of the action is, right? So you want to know, we saw that you'd have like flow and then a plateau. If you look at G prime, then there's another case of flow in the Rouse dynamics. This is within the tube, G prime versus frequency, right? So in the tube, then you see flow again. So you want to see that to know how things are happening on a nanoscale. So this is nano, this is micron millimeter, say, over here. So you're going across huge size spans in a viscometer, right? G double prime, that's going to cross over again over here, whatever. So right, so you can have two crossovers, one here for the viscoelastic relaxation, and this is the tube relaxation at the high end. So your mechanical viscometer is going to cut off like here. Okay, so that means you don't get this information. So you want something that could go to really high frequency or beyond where these mechanical things could work. In the 1990s, someone figured out how to do this. Weiss was a guy at Harvard, and there's a guy named Pine who went to Penn afterwards, right? They worked with Weiss and they developed this technique. So basically they stuffed a bunch of colloidal silica into a sample, like it could be a polymer melt, it could be a solution. And then they watch those particles move around. So they have to put in enough so they get multiple scatterings, so it's completely white, right? Multiple scattering is a big part of this technique. Then they do a dynamic light scattering measurement. So they measure this noise pattern, and they get a G2, a decay function, and then you can relate that G2 to the motion of the particles. This is a hyperlink. It goes to like kind of a wiki page that shows this video. So at different time scales, the particle is probing different parts of the structure. It's hitting, say it's in a gel or a network of polymers, it's hitting the polymers that slows it down. So at some time scales it can fly through, and some size scales it's trapped, right? So at short time scales, it's probing the smaller sizes, it gets stuck, and at long time scales it can get through the thing, right? That's kind of the idea. So your particles are probing the flow around these. So the viscosity of the solid is telling you so it's basically, if it's diffusive motion, the mean squared displacement of that particle is going to follow time to the power to linear, right? Because this is mean squared, so it's squared. So it's r squared versus time, that's proportional for Brownian motion. If it meets some kind of barriers, then that thing drops off. right? So you get a slower, you get a less mean square displacement because it's confined, right? So then it goes to flow at long times when it has time enough to escape the thing. So at low times, you're looking at small sizes, you're looking at this bouncing in this network, right? And again, 1 over time is going to be frequencies. So these are really high frequencies, much higher than you can get with a mechanical rheometer. And all you're doing is let the particle move with KT and probe the structure, right? So from this mean square displacement, oops, I shouldn't have done that. That's the wrong place. You know, like right after you do something, that was the wrong thing to do. So basically, you do a Laplace transform, which is this kind of idea. So you take the time domain, exponential minus frequency time, that gives you the frequency domain, and this frequency domain. So this f of t is your kind of your noise pattern. Then you do a frequency domain, and you find out that you can get this mean square displacement out of this. And the mean square displacement, say, if it's Brownian motion, is going to follow t, and if it's stuck like purely elastic, it's going to be a constant. So you can break apart this g of s into g prime, g double prime, because you're probing different frequencies in this, right? So you kind of seeing this. We saw with the dynamic light scattering that we were looking across frequency, wherever that is. 44. That is like here. So we're looking at different times, and this is a frequency plot. So you get many different frequencies, right? So you can probe many different frequencies in this Laplace transform of the decay function, get this function out of it. But the math is dicey. There's a lot of math involved. It's going to involve this kind of integral. Backscatter is easier than forward scattering, so these tend to be backscatter instruments. And then because of the path length matters for multiple scattering, so if it's forward scattering, you have this path length in it, this L star, and the path length disappears for backscatter for some reason. So basically, this is going to convert like this mean square displacement. Those math will convert the mean square displacement into G prime, G double prime, just as exactly what you get from mechanical rheometry. You can just tag these curves onto your mechanical rheometry curves and get this expansion of the frequency scale and get into this range where you can see the local structure, like the diffusion within the tube. So you can explore the tube model. You can look at how motion within the tube for different polymers happens. So that becomes kind of useful for some people. So if you want to model rheology, this is vital information. Because if you want to model the rheology, the flow of something like polyethylene, you have to start somewhere, right? And the place you want to start is the Kuhn unit, right? You want to start at least at LK, if not below. And then you want to hook up the Kuhn units, and then you want to see the tube diameter, right? And then you want, so you're putting together a model that's got these pieces in it, so you can talk about the bulk viscosity out at really low frequency. But you have to start with the high frequency response and then build it up. Right? So if you don't have measurements out here, you can't do that. Right. So all the simulation is going to start with the Kuhn length, then the tube diameter, and then go through this plateau modulus, and then right to predict the whole thing. So in order to do that, you need to have this information, need some measurements to verify what you're guessing. And this machine will give that to you. Right, so that's one thing. Then another thing that's related to this is quasi-elastic neutron and X-ray scattering. So this dynamic light scattering and the DWS are things that can fit. They're about the size of a computer. They can fit on a desk, right? These quasi-elastic neutron scattering things are not. They're big. They're the size of a building. So the dynamic light scattering machine is going to set you back about $50,000, right? The neutron scattering facility cost $1 billion, 1 billion, right? So there's a big price difference. So there's some question about how many dynamic light scattering instruments could you buy for one quasi-elastic neutron scattering instrument. So this is going to be a building. These are people. Like that little red thing is a person, right? So you can blow that up. So that's kind of the scale of these things. This is one instrument. So this would be like one DLS instrument to do quasi-elastic neutron scattering. So backscatter. So the beam hits a sample and it's got this backwards detection. And it's a huge machine. There's a picture. It's kind of a picture of the outdoors of this. This is the this is kind of a outline of it also. So there's a target that makes neutrons and they fly down a tube and there's a detector down here. And the distance of that is a football field, maybe a little bit longer. Right, so this is pretty big. This is a picture of the this is a graphic of the SNS spallation neutron source in Oak Ridge. So this is a particle accelerator. They come along here and the particles come, and then they in the middle of this building as a target, so it goes underground, hits the target, and then neutrons are splayed off. It's a spallation source. And then the neutrons go through some kind of moderator, and those instruments come off. These quasi-elastic instruments are the longest ones. They come out of the building, right? And then there's other kinds of like neutron scattering, small angle neutron scattering, diffraction all inside this building. So this is like a big warehouse full of equipment centered around this target. They're currently building another target. So this cost $1 billion to build, 1 billion, right? So $1,000 million to build this. So, and then in this background side is where the centrifuges are to make plutonium, enriched uranium and plutonium, right? So right on the other side of this is a Y12 plant where they make nuclear bomb materials. I'm not sure if they're doing that now, but basically that's where they do it. So it's kind of like on the other one side of the fence is this research lab, on the other side is this bomb factory, right? So anyway, they're building another $1 billion for another target source here. So that this is so popular, they're building another one next to it, right? So when you go here, so you just apply for time on this. When you go here, you stay at this guest house, which is not on this map, I guess. It's actually, guest house is right down here. There's a little hotel they have. You can stay there because this is a little bit, it's about 20 minutes from the town of Oak Ridge. It's in the woods, you can see. So anyway, this other facilities, there's two actually at Oak Ridge. Is a reactor that makes neutrons, and there's a spallation source. And then there's a reactor in NIST in Washington, D.C. And that's it for the US. There used to be a source at Argonne in Chicago and a source at Brookhaven in New York, near New York City. But they don't exist anymore. And then there's sources in Europe. There's the biggest one is the ILL in Grenoble, France, and in the Netherlands. They have another duplicate of this in the Netherlands that they built. And then Japan has neutron sources, and Britain has smaller ones. There's one in Italy. There's a bunch of them. So China has one near Hong Kong. One of my grad students is working there. And then, ex-grad student. And then, so there's these sources all over the world. Korea has one. Japan has a bunch. So yeah, Australia has one. So these facilities are around. Anyway, so what is it? So in the early days, when they wanted to do this, or when this idea of like quasi-elastic measurements came up for light, right? There were two camps, right? And there were two camps. And the first camp that really won out was just kind of using the Doppler effect. So the light comes in. So with the Doppler effect, you have a train going by and it's blowing its whistle. However you draw a train, it's going by and it's blowing its whistle, and you hear like a certain frequency, right? So there's a frequency shift when it's coming. It seems to be a higher frequency. So you get that pitch approaching, and then when it's at near you and then departing, it's a lower pitch. It goes as it goes by, right? So this is kind of the amplitude versus a frequency, and this is time 1, time 0, time -1, whatever. Right. So frequency changes as it flies by, and that tells you how fast the train is going. Like if you measured these frequencies the difference in that delta frequency would equal the speed of the train, right? Because the speed of sound is kind of within the range of the speed of the train. So there's a significant effect of the train in the sound, right? The same goes with these particles. The speed of the particles is about the frequency of light or the size, the wavelength of light. So the distance a particle travels as you look at it in the beam is related to about a microns. Right, so it's similar to the wavelength of light. So as these particles fly by, there's a shift in the wavelength of light since they're moving in both directions. So if you had a perfectly monochromatic light, say if you had a laser, right? So once they had lasers, they could do this. Then once the particles were in there, you'd see that it would have this shoulder on it that has to do with the trains flying by. This is wavelength, this is amplitude, right? So you get maybe a diminishing of the peak and the broadening of the pattern. And the amount of that broadening is an exponential decay. So it's going to be like exponential minus lambda over some kind of correlation length, right? So basically from that broadening, so that's called quasi-elastic light scattering, or QELS. So that was a competitor to DLS, right? And DLS, we're looking at this as it flies by, it flickers. So you get this time. And originally, like this was much easier to do because you could make all you need is a monochromator to get this pattern, right? So, and then DLS, you had to have a computer and it would take like a long time to analyze the data. So QELS was first in to get these relaxation times, tau. It won, right up for about 3 years. This was the main tool. And then people invented this computer correlator that could spit out the answer immediately. And then it was realized like this DLS is a much better technique to use to get the same information, right? So there's two ways to get it, to look at this, right? So in neutrons, everything is, so in neutrons, people use this quasi-elastic because they basically you can't get monochromatic because it's neutrons, it's not a laser. And then it's easier to measure it this way for some reason. I'm not really sure, but basically they tend to use this quasi-elastic. Then they'll use something called spin echo that has to do with neutrons are polarized. So you can look at, and the polarization rotates as it flies down a tube. You can look at how you can use polarizers to kind of analyze the interaction of the neutron with whatever's in there, and that because the polarization is rotating, there's a time constant with it. You can measure the time constant of materials. It's called spin echo technique, right? So that's a related technique, but basically quasi-elastic neutron is directly related to dynamic light scattering. It's analyzed the same way. You get a relaxation time. From that, you look at Brownian motion, you get the diffusion coefficient, you get something like a hydrodynamic radius. So it's directly linked to DLS. So it's kind of DLS for neutrons. So it's DLS for where the beam is an angstrom or 10 angstrom, one nanometer beams. And for X-rays, it's 1 angstrom beams, right? So neutron, because you can tag the molecules also, so you can light up certain parts of a complex structure. So you have a cell with all kinds of ribosomes and whatever, and a nucleus in it. They want to look at just what happens to this one protein, right? So I can deuterate that protein, and then I can stick it into a QELS, and I can tell you what the diffusion coefficient of that protein is under different conditions, like when the cell's active, when it's not active, right? And from that, I can tell the biological function of the cell, right? You could put anything in the beam because a neutron beam in this place is going to be about that size. It's big. The neutron beam's about 1 centimeter, and the path length in it is going to be, could also be 1 centimeter. Right, so you have 1 centimeter cubed. You can put a lot of things in a neutron beam. Also, it doesn't matter. Like you can put anything completely black. You can put steel in here. You can put the beam goes straight through because it's uncharged. Like a neutron is an uncharged particle. It flies right through anything. So basically, there's a lot of advantages to neutrons over light. You don't have to be able to see through it to use neutrons. You can use much larger samples. Anyway, there's various reasons that people use it. And then the biggest one probably is that you can tag with deuterium. So you can replace hydrogen with deuterium and make things light up and then see only certain features, right? So anyway, so this is the picture. So you have the elastic means the energy is exactly the same, or the energy of the wavelength is exactly the same. Quasi-elastic means you've lost some due to this Doppler effect. And inelastic means that there was a shift. There's like actually a shift. So it's still the same sharp peak, but it's moved over. Right, so we're looking at quasi-elastic. So you look at right near the peak and high resolution of the energy. That's the kind of thing you need. And then like say you have, you want to look at just lithium ions moving through a lithium battery versus protons. What's the charge carrier? You can tell with this. Polymer motion on like, you know, the reptation tube was discovered this way. Biology, like what's the function of water, how does it interact with proteins? So there's a lot of like molecular scale. So this guy, John Nichols, in the chemical engineering department, this is the main tool he uses. Like he uses a lot of quasi-elastic neutron scattering. He also uses dynamic light scattering to look at things. This is just showing the spectrum. So there's always a background in neutrons due to incoherent scattering. And there's a peak due to the diffraction peak, or there's a single wavelength that you have. Sorry, this is just looking at the spectrum. So it's just a one wavelength, and then there's this Gaussian kind of looking, it's really Lorentzian spread due to the quasi-elastic interaction, right? And you can fit that data and separate the components. And then this is just showing like the time scales you can get with this technique. So again, like these are actually different instruments. These are all at that $1 billion facility in Oak Ridge. So there's they cover different time scales and different Q scales. So this is a size they're probing. So Q of 1 is about Q of 1 is basically 1 angstrom, right? And this is 1 nanometer. That's 100 nanometers, or 10 nanometers. Then this is 1/10 of a nanometer, so 1 angstrom. And this is 1/10 of an angstrom, right? So you can probe different size scales with this. And then the time scales have a huge range, right? This is milliseconds. This is so you go from this goes to like pico and below, right? And then to nano, pico, millis way up here, right? So basically there's a wide range. You can go from the DLS time scales all the way to 10 orders of magnitude smaller with this, right? So you can look at molecular scale or submolecular scale relaxations all the way up to entire polymers moving around, right? See, so there's a huge range of, so you can probe. And then the different instruments you need to use to access those, right? So these are all available. So you'll see data once in a while like this. I mean, anyway, it's basically going to be broadening of the peak. Right? That's kind of what you're looking at. This is looking at side groups on this. This is called POS. I think this is called, yeah, POS. So it's polyortho something silicate. So these are the original nanoparticle. This is PDMS made into a nanoparticle. So it's SI. You can put side groups on it, and they want to know about the motion of the side groups. So they deuterate those. Then they look at the mean square displacement, what we got from the dynamic light scattering versus temperature. And they see when those things start moving, right? And then they get to a region where they see Brownian motion of those things. So basically, this is almost like a time dependent DSC, or thermal calorimetry measurement. So you can look at motion of the molecules different times. So this is what Nichols does. He does this kind of thing all the time. He's got a lot of papers in this area. You can look at something like, there's a lot of different things, but say you have a membrane and you want to do separation to purify water. So you want to see how the ions move inside the membrane pores. So you can measure that with this technique. These are some data on membrane showing the diffusion coefficient. We're showing that this breadth of the peak versus Q. So you can find a size scale So this, what size is the membrane separating? It's separating things where the thing stops moving, so there's no breadth to the peak, and then things bigger than that move freely through. You can see it's Q squared here because that's Brownian motion. And then they're fitting this, the culminant, this gamma. Just like in dynamic light scattering, use the same term. It's 1 over tau, right? So there's different kinds of motion. They look at rotational doesn't change, and then this kind of translational does change. So basically, you're looking at the trapping of the molecules in the pores of this thing. Anyway, so that's kind of it for this thing. This shows that where this material they've actually looked at, because it's important for water purification. So they've looked at it on 1, 2, 3, 4, 5, 6 different instruments, all at the SNS and Oak Ridge, and they can get these diffusion coefficients at different size scales, or different relaxation times. So how does the diffusion coefficient change for this material? That's about all we have time for today. So I wanted to go through our G by RH ratio, but I think we've already kind of talked about that. I think we've already pretty much looked at that a little bit. There's a table of the values. I don't think we really need to do it. This is for branching. F is the branch, number of branches. We already looked at this pin polyamine isopropyl acrylamide data. We looked at that earlier on. There's a quiz about that. That's like so that's kind of it for dynamic light scattering. So next time we're going to talk about a different topic, like look at how polymers respond to external perturbation. So that's got to do with the topic called blob theory. So probably like the week we'll talk about blobs. So anyway, I'll have a quiz on Friday at 10, hopefully. I'll email it out, and then if you have any questions, email me. So have a good week. I'll talk to you later.